It's my pleasure to give a talk at this year's STOC. In this talk, I'll describe recent progress in the study of random constraint satisfaction problems. This is joint work with Alan Sly. So I'll discuss constraint satisfaction problems, or in short, CSP. And these problems come from combinatorics and theoretical computer science. And it addresses this question: is it possible to assign values to a set of variables to satisfy a given set of constraints? These problems include system of linear equations, finding a proper coloring of a graph, or finding an independent set of a graph, or satisfying a Boolean formula. And I'll discuss random constraint satisfaction problem, where the focus is to investigate properties when the constraints are chosen randomly. Perhaps the canonical random constraint satisfaction problem is the random K-set model, which is a model of random Boolean formula. And it's defined as follows. We have n variables, x1 to xn, which belongs to either true or false, or equivalently plus or minus, and they're subject to m constraints. And each constraint is represented by a clause, and these clauses takes the order of k variables uniformly chosen from plus minus x1 to plus minus xn. So these are random constraints. For example, a three-step formula with 5 variables and 4 clauses looks like following. So we want to assign x1 to plus or minus to x1 to x5 so that it satisfies every clause. And these clauses are represented by these parentheses. And the K-set model is parameterized by the density of the clauses, which I'll denote by alpha, which is m over n, which is number of constraints per number of variables. There's a natural graphical description of this K-set model, where this K-set formula can be represented as a bipartite sine graph. For example, take this 4-step formula with 3 clauses as follows. This can be represented by this bipartite sine graph. And on the top, we put all the clauses, all 3 clauses, and on the bottom, we put all 7 variables. And if a variable participates in a clause, then we connect them. And we need to encode how this variable participates in a clause, and that is represented by a literal, which are either plus or minus, which lives on the edges. For example, the first clause is plus x1 or plus x3 or minus x5 or minus x7. So the first clause is connected to first and third and fifth and seventh variable, where we put plus literals on the first 2 edges and the minus literals on the last 2 edges. So the constraint that this clause puts is that the first and third and fifth and seventh variable cannot be minus minus plus plus. And since this is a 4-sat, this means that every clause has degree 4. In this talk, I'll discuss a variant of this K-set model called random regular null-equal set model. And given a K-set formula, an assignment x is a null-equal set solution if both x and minus x are satisfying. So this null-equal set formula has more constraints than the K-set model. I'll consider random d-regular k null-equal set instance, and here d-regular means that every variable participates in the same number of clauses, namely d clauses. And this instance is chosen uniformly from all the k, d bipartite graph with uniformly chosen literals, where we take mk equals nd. For example, if you consider m and n equals to 6 and k and d equals to 3, this random graph can be described as follows. We put 6 clauses on the top, 6 variables on the bottom, and we put 3 hanging half edges on each clause and each variables. And out of the 18 half edges on the top and 18 half edges on the bottom, we do uniformly at random matching between these 2 set of half edges. And then after then, we put uniform random plus minus signs on the edges. So the resulting sign bipartite graph looks as follows. Here we take k and d to be fixed, and let n and m goes to infinity. Then, since the degree of each clause, which is k, and each variable, which is d, is fixed, and let n and m goes to infinity, the resulting graph will be sparse. Namely, it will be locally tree-like, which means that there are few number of short cycles. And given this graph, we want to understand if we can assign plus or minus to the x1 to x6 so that it satisfies every clauses. And here for the null set model, the constraint that the first clause puts is that x1, x2, x3 cannot be plus plus minus nor minus minus plus. And this model possesses extra plus minus symmetry, which makes it more mathematical tractable than the K-set model. But the key point is that this model is predicted to have the same qualitative behavior as the random K-set model. And I'll elaborate on this point later on. So given this setup, one can ask for which values of alpha are there satisfying assignments. So since alpha is the number of constraints per number of variables, if you increase alpha, the probability of having a solution decreases. And actually, numerical experiments suggest that for all k greater than or equal to 3, there exists a sharp threshold alpha star of k, such that if alpha is below this threshold, there is a solution with high probability, whereas if alpha crosses the threshold, there is no solution with high probability. Namely, the probability of having a solution quickly drops from 1 to 0 as alpha crosses this threshold. And the question is, can we prove such sharp threshold, and can we characterize this alpha star of k? One can also ask many more refined questions. For example, algorithmic, can solutions be found efficiently? Also free energy, how many solutions are there? And also overlaps, what does the joint distribution of the several solutions look like? And also geometry, how does the individual solutions look like? And the new result of in this talk will be about this geometry. So recall that these solutions live on this bipartite graph, so we can discuss how these plus or minus are located within this graph. There's a local geometry question to this model. Starting from early 2000s, there's been groundbreaking predictions from statistical physics. And statistical physicists in particular suggest that many random constraint satisfaction problems can be recast as mean-field spin glasses on sparse graphs. And their predictions are what's called replica symmetry breaking predictions, which were developed to study dense spin glasses such as Sherrington-Kirkpatrick model, which goes back to the work of Parisi in 1979. And their predictions for random CSPs are called one-step replica symmetry breaking predictions, which means that there's one level of clustering of assignments. One highlight is that physicists predict universality for many of the models in random CSPs, namely Q-coloring on random graphs, which is an example of random CSP, and also the models that we discussed, random regular non-equal set model, and random K-set model for Q and K greater than 3 is predicted to be in the same 1 RSB class. And what does this 1 RSB class mean? This is the conjecture phase diagram from Prasakala et al. In 2007. And in this picture, from left to right, we are increasing alpha. So we are increasing the number of constraints. So there are less and less number of solutions. And each box represents the geometry of the solutions where you look at the solution space at a given alpha. And what these black blobs represent is a connected component of the solution space. Here, let's connect two solutions if they differ in one variable. This gives us a connected structure of the solution space. And then the cluster is defined to be a connected component of the solution space. So two solutions are in the same black blob if there is a solution path that connects the two. When alpha is very low, there are not many constraints, so there's a lot of freedom to move around. So solution space start out as a well-connected cluster. And there's a conjecture phase transition called alpha cluster, such that all out of a sudden, the solution space quickly decomposes into exponentially many clusters. And this was partially verified by this seminal paper by Aklioptas and Kojawa in 2010. And this cluster regime, if you sample two uniform solutions given the instance, they will typically be very far apart. They'll behave as almost independent. And this is what physics call replica symmetry regime. In particular, if you look at the Hamming distance, normalized Hamming distance between these two solutions, it is conjectured that it will concentrate on 1/2. There's another phase transition called alpha condensation, where suddenly the exponentially many clusters are condensed into large clusters. Now solution space is dominated by a few largest clusters, one largest clusters. And in this regime, if you sample two uniform solutions, there's non-negligible probability of being in them in the same cluster, in which case they're correlated. And this marks the onset of long-range correlations, which is very interesting from a mathematical point of view. And this regime is called replica symmetry breaking regime. Finally, after alpha SAT, there is no solution with high probability. And this models are called 1-RSB because in the condensed regime, if you measure the normalized inner product of two uniform solutions, they concentrate on 2 points according to whether these two solutions are in the same clusters or in a different cluster. So recently there has been a lot of mathematical progress in understanding such phase diagram of this random constraint satisfaction problem. In particular, by now we know many results for random regular non-equal set model. And in particular, we know the condensation picture. For large K, we know that if alpha belongs to this condensation regime, then with high probability, we know that this largest clusters, O1 number of clusters, occupy most of the solutions. And if you measure overlap of two uniform solutions, they concentrate on 2 points, namely 0, which means that two solutions are in a different cluster, so they will be far apart, or P star of alpha, in which case the two solutions are in the same cluster. And these happen also with constant probability. And the threshold, the condensation threshold and the satisfiability threshold for the non-equal set model are determined by a fixed point of a recursion. And this were verified by Bing-Sly and Sun, and Sly, Sun, and Zhang. And also, we know that for many random constraint satisfaction problems, including non-equal set model, if alpha is below condensation threshold, then the overlap concentrates around 0. And this was verified by Kojawa et al. So there's a phase transition happening at the condensation threshold. So the new result in this field is about local geometry of non-equal set solution. So given the instance G, let's consider depth T neighborhood of a variable V. So since G is a graph, we can talk about distances of a variable. And because of the sparsity of the graph, sparsity of G, this partial VT for most V will be isomorphic to a DK regular tree. For example, if D and K equals 3 and T equals 2, this looks like the following. Now, we can ask, if you draw uniformly at random solutions, how are these plus or minus configurations on this tree look like? Namely, let X be a uniformly drawn non-equal set solution. Then the local geometry, which is also called local weak limit, at level T can be described by empirical distribution of x restricted to partial VT. So this is the empirical measure on this plus minus configuration on this tree. So this is a random element of in the space of probability measure on plus minus configuration on this tree. One can ask, what does this random element converge as n goes to infinity? And if so, can we characterize this limit? Next, I'll discuss the local weak limit below condensation. And for alpha below condensation threshold, there's no long-range correlation. That is to say, the causes outside of this tree has little effect on the inside of the tree. And it was verified by Kajaglan et al. That the local weak limit below condensation is indeed given by the uniform measure on this tree. Namely, the causes outside this tree has no effect on this inside the tree. And this is because below condensation threshold, there's no long-range correlations. And also, this uniform measure can be described in a simple manner by a Markovian fashion. This is also called broadcast process. Here, choose the value x rho at the root rho uniformly at random. Then, for each d clauses adjacent to rho, independently draw a non-equal set solution around them for each clauses, and then we go downwards. We repeat until tth level. So this can be described by a simple Markovian process. In this new result, we show that if alpha's in this condensation regime, because of long-range correlations, this local weak limit is no longer Markovian. And we can characterize this local weak limit by an explicit non-Markovian process. Moreover, the convergence holds with n to the minus 1/2 fluctuations. And this is the first characterization of local weak limit for random CSPs in the presence of long-range correlations. And this local weak limit is described by a fixed point to a distributional recursion. Finally, I'll end the talk by mentioning some open problems. First of all, most of the mathematical progress has been unfortunately restricted to large enough k, and many of the conjectured behavior, including local weak limit, is conjectured to have the same answer for a case as small as k equals 3, and this is a wide open problem. One can also discuss extension of this condensation phenomenon and the local weak limit for to other models such as random graph coloring and the K-SAT model and finite temperature models. Also, one can ask about the unified approach to models in 1RSB class. So far, there's been our study has been divided into model-specific techniques, and it would be nice to have a result that a proof technique that can deal with many models in 1RSB class. Also, there's a refined conjecture from statistical physics that the weight of the cluster in the condensation regime follows a Poisson-Dirichlet distribution, and this is also a wide open problem, which would be very interesting to establish. Finally, it would be very interesting to establish efficient algorithms for finding or sampling a solution, and also understanding matching algorithmic hardness for these problems. Thank you for listening.